All right, everybody, welcome to our first math video. This time we are going to be starting with section 1.1. We're going to be discussing sigma notation today and how we can use that to simplify some ways of writing out sums. So I'm going to start maybe by talking about our end goal of this chapter, which is to come up with a general method for computing areas and volumes. These two things are really useful. Certainly you can imagine that if you're in some kind of engineering world, you want to make some kind of new structural component of something, you probably want to know how much space it takes up. And if you're making a strangely shaped piece, perhaps then it's not obvious. We can't use something as simple as the volume formula for a cylinder to compute its volume if it's not a cylinder. So certainly we want some kind of general method for computing areas and volumes. This is of practical interest to us. Perhaps the thing that's not clear right now is how on earth this relates to calculus. I mean, you know, in 251 we talk a lot about derivatives, and we have this nice geometric interpretation of a derivative as a slope. But what does that have to do with areas or volumes or anything like that? So that's really what that connection is going to be what this chapter is exploring. The assumption that we make is going to be a fairly innocuous one. It's going to be simply that if we have some kind of rectangle, let's draw a better rectangle here, maybe with side lengths, we can say L and H, then the area of the rectangle is equal to L times H. So again, this is something that, you know, maybe we first saw this area formula in elementary or middle school or something like that. And so this is kind of the one thing that we're going to start with. But before we actually start talking about computing areas and volumes, we're going to need a little bit better notation. Eventually what we're going to do is we're going to maybe take some curved shape, and we're going to approximate that curved shape with a bunch of different rectangles. And we're going to want those rectangles to be fairly small, and we're going to want to add up all the areas of those rectangles. Now, writing out sums is a little bit cumbersome, as we'll see in this first example here, so we're going to try to develop first some notation to make things look a little bit more elegant. So let's see. So we have this first example here asking us what is the sum of the squares of the integers from 1 to 10. And if I were simply to take a moment to write this down, we would have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared. But if you go through and you actually plug all of these numbers into a calculator, you find that the answer is 385. Great. So, like I said, a little bit cumbersome, and even more cumbersome because there's like a nice pattern here, right? I mean, we're not like adding up a bunch of random numbers. We're adding up numbers that have some kind of pattern associated with them. So we want some way of writing this out more simply. So the way that we're going to do that is first I'm going to just write out the notation that we're going to use, and then I'm going to explain how it works after I've written it. So what I'm going to write here is, this is first the Greek letter sigma. Below it I'm going to write I equals 1. Above it I'm going to write 10. And afterwards I'm going to write I squared. So what exactly, let's kind of break down this notation and talk a little bit about what it means. So this sigma here is the Greek equivalent of our English letter S, which of course stands for sum for us. So that's sort of where that starts. So this is indicating that there is a sum going on here. This subscript, this I equals 1 here, we can... let's see, that I equals 1 is going to indicate the starting value of I. On top, we have this 10, And this 10 here is going to indicate the ending value of I. And last, we have this I squared thing, which for us is going to indicate, let's put that in black. We have this I squared here, which for us is going to represent the thing that we're adding up. So procedurally, when you come across a sequence of symbols that looks like this with some kind of symbol with some kind of sigma notation, what you're going to do is you're going to say, well, the first thing that I'm going to do is I'm going to start at this I value here. So this whatever is below the sum, I'm going to take that to be my I value, and I'm going to replace the expression here with that I value. I'm going to use that I value in this expression. So for me, this tells me start at 1 for I, and then replace I with that starting I value in the expression. So here the expression is I squared, so I'm going to replace I by 1 and write down 1 squared. Next, what I'm going to do is I'm going to increment I, increasing it by 1, and making sure that I'm not going above the top value here, the ending value of I. So if I increase I by 1 from where I started, I'm starting at I equals 1. If I increase it by 1, I get up to 2. 2 is not bigger than 10, and so I'm going to go ahead and replace I squared, or replace I by 2 now. So in that case, so we'll have plus because this is a sum, and now I'm going to replace I by 2, so plus 2 squared. I'm going to continue again. I'm going to ask the question, okay, what's the next I value? Well, I've done I equals 1 and I've done I equals 2. So now we want to think about what happens to I equals 3. 3 again is not less than 10, or is not more than 10, sorry. And so we can again replace my value of I in the expression by the number 3. So that's 3 squared. And we continue this process of increasing I by 1 up until we get to the ending value of I here. So you can kind of see the pattern here. I'm going to keep adding 4 squared. I'm going to add 5 squared. I'm going to add 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared here. So we have all of kind of these pieces working together here. This sigma tells me add. This I equals 1 says start with an I value of 1. This 10 on top here says stop with an I value of 10. And I squared tells me exactly what I'm going to be adding up. So let's do a couple of examples here. All right, so example 3 is asking us compute the sum from I equals 1 to 5 of I cubed. So again, I'll think about, okay, I equals 1 is my starting I value. So we'll go ahead and replace I by 1 here. So 1 cubed. Then I'm going to increase I by 1. So I equals 1 was my first step. So I equals 2 is my second step. So now I'll add to this, let's see, 2 cubed. And to this I'll add, I'm going to increase I again. I goes up to 3 now this time. So 3 cubed. And I keep doing this up until I get to I equals 5. So plus 4 cubed, plus 5 cubed. And if I add up all of these numbers and you plug it into a calculator, you're going to get 225 out. Great. All right. First example done. Let's do something a little bit more complicated here. So we're now looking at the sum from I equals 3 to 5 of I squared minus 2i. So we've got my starting I value down here at I equals 3. So I'm going to go ahead and start by replacing all of my i's by 3's. So I've got 3 squared minus 2 times 3. Let's make that minus better. Now to that expression, I'm going to add, I'm going to increase I by 1 this time. And so increasing I by 1 gets me up to I equals 4. So if I replace I by 4, I'm looking at something like 4 squared minus 2 times 4. And now I'm going to increase I by 1 again. 5 is my highest value for I here, and so I'm going to stop here at 5 squared. Let's do a better 2. 5 squared minus 2 times 5. Let's actually write a minus sign. All right, cool. So we have our sum. I've started at my starting value. I've increased I by 1 at each stage, added up all the numbers, stopped at I equals 5, and if you plug this into a calculator, you get out the number 26. Great. So maybe not too exciting so far. We've got one more example that we can do. So here we're interested in we have some starting values for A, or for the A sub somethings, and we want to compute this sum from I equals 1 to 5 of AI. So this is a little bit different because this expression here, the things that we're adding up, aren't just numbers kind of that depend, or they are numbers that depend on I, but they're not like arithmetic combinations of i's. It's not like we're taking I squared here. We're using I as a subscript to indicate which of these numbers we want to grab. So here it's going to say, when we're doing this sum from I equals 1 to 5 of AI, we're going to start with, it's going to be the exact same process. So we're going to start with I equals 1, and I'm going to replace all of the i's that I see in this expression by 1. So that's going to look like I equals 1 to 5, AI. This is going to be equal to, well, I'm going to start with A1. And then to that, I'm going to add now. Well, I increase my I value by 1, so I increase it to 2. So I add on A2. Next, I'm going to add on A3, and I continue doing this until I get to 5. So plus A4 plus A5. And if we look at the values that were given for all of these numbers, A1 here is 2. A2 is minus 5. A3 is 8. A4 is minus 9. A5 is 2. And those are all of the numbers that we need. And if we add all of these numbers up, we're going to get out minus 2. So here's kind of an example, first showing us that it is possible to get negative numbers out of a sum. And also kind of a nice example because we have something that isn't a kind of, like I said earlier, it's not an expression that depends on, or it is an expression that depends on I, but we're not like multiplying I by anything here. We're just using I to indicate which numbers we're going to grab. All right, so there's an example 6 here. Let f of x be the square root of x, and we want to compute this sum. I'm going to let you work on this, and I'll come back to this at the beginning of the next video. So take a moment to work on this, and you can check out the solution next. But let's look at a different class of examples that we might see with sigma notation here. So example 7 is asking us to use sigma notation to write down the sum 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 18 plus 20 plus 22. So we're not actually trying to compute this number here. We're just trying to rewrite it in kind of a shorter form using our new sigma notation. So the first thing whenever we're given something like this is we want to look at the pattern of the different numbers that we're adding up here. So notice that as I kind of increase, as I go on to the next number, I'm adding 2 here. 10 is going to also be 2 plus 8. 12 is going to be 2 plus 10, and so on and so on and so on. I'm just adding up a bunch of consecutive even numbers here. And so the way that I want to think about this then is, well, I'm adding up a bunch of numbers, and I'm adding up a bunch of even numbers, which means that they're all multiples of 2. So the things that I'm adding up are 2 times some number I here. In order to get the subscript and the superscript on my sigma here, I want to think about, well, what's the I value that I'm starting at? And since the first number in my sum is 6 here, and the thing that I am adding up is this expression 2i, then the first I value that I'm going to have is 3. Because if I start with I equals 3, the first item in my sum is going to be 2 times 3, which is exactly the 6 that we're looking for here. Now I'm adding up all of these consecutive multiples of 2, and I keep going until I get to 22. And so in order to know when to stop with this sum, I want to think 22 is 2 times what? And it is 2 times 11. So I want 11 to be there at the top of that sum. So again, not really interested in knowing what this number is, instead just in kind of writing it using this, this shorter method. All right, example 8, use sigma notation to write down the sum 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. There's no, I mean, we are adding up a bunch of even numbers here, but we're certainly skipping a bunch of them. Maybe the pattern that we want to recognize here is each time I move to the right kind of one summand, so the different components of the sum are called summands. Every time I move to the right and consider a new summand, I am multiplying the previous one by 2. So if I go from 1 to 2, that's multiplying by 2. If I go from 2 to 4, that's multiplying by 2. 4 to 8 is multiplying by 2, and so on. So here what I'm looking at, instead of multiples of 2, I'm looking at the powers of 2. In fact, 1 I know is 2 to the 0 power. 2 is 2 to the first power. 4 is 2 to the second power. 8 is 2 to the third power, and so on, up until we get to 64, which is what? We've got 8 is 2 to the third, 16 is 2 to the 4, 32 is 2 to the 5, and 64 is going to be 2 to the 6th power. Cool. So if I want to use sigma notation here, then I want a sum, and I want to be looking at 2 to the power of the index. The letter I here stands for the word index. So I'm starting at 2 to the 0, so I want I to begin at 0. And I am going all the way up, and I'm adding all the way up to 2 to the 6th power, so my superscript on the sigma is a 6. And you can verify if I were to ask you the question, write out the sum. If I were to ask you to do this computation, you would write out 2 to the 0 plus 2 to the 1 plus 2 to the 3, or 2 to the 2 plus 2 to the 3, and so on. All right, so we have another example here. So use sigma notation to write down the sum 0.4 plus 0.1 plus 0 plus 0.1, and so on. And I think I am, again, going to leave this for you to do at the moment, and I will come back to this in the next video. So go ahead and take a look at that problem and see the solution next. Now, the next thing that I want to do is share kind of an interesting mathematical tidbit. So this next page here is not going to be on an exam. You're not going to be tested on this, but I think it's kind of there's a fun historic story and also some sort of interesting math that's going on here. So kind of legend has it that a mathematician by the name of Euler, which for reference is spelled E-U-L-E-R and pronounced Euler, or at least it's roughly pronounced that way. So anyway, so legend has it that when he was a kid, his school teacher got kind of fed up with some of his antics, and in order to keep him busy for a while, asked him this question here: what is the sum of the integers from 1 to 100? So certainly, if you do this problem kind of naively and you just start writing down the numbers from 1 to 100 and you try to like add them all up, it's going to take you a little while. So this was the task that the teacher intended for Euler to do in order to just keep him occupied so he would be out of the teacher's hair for a little while. But Euler, who grew up to be one of the best mathematicians in history, had a cleverer idea when solving this problem. So Euler said, well, you know, if we're thinking about this sum that we have here, 1 plus 2 plus 3 plus 4 plus so on, all the way up to, maybe let's go up to 97 plus 98 plus 99 plus 100, let's, instead of starting by adding up 1 and 2 and then adding that to 3 and 4 and so on, he said, well, let's actually draw the connection here, and let's start by adding up 1 and 100. And if we do that, we get the number 101. And similarly, we can add up 2 to 99. And if we do that, we get the number 101. And we can add 3 to 98, and that gets us another 101. And we can add 4 to 97, and that gets us another 101. And we can keep doing this, and keep doing this, and keep doing this, until we kind of get down to something like a 50 in the middle. 50 and 51, I believe, are the numbers that you're pairing together there. So all of these pairs of numbers add up to 101. And if we ask the question, how many pairs are there? So we ask the question, how many pairs are there? Well, we see that we're pairing 2 numbers at a time, and there are 100 numbers in this entire list here. And so we end up answering the question that there are 50 pairs. All of those pairs add up to 100. And so this tells me that, in fact, the total sum is equal to the number of pairs, 50, times the sum of each of those pairs. So 50 times 101 is equal to 50 times 100 is 5,000, and 50 times 1 is 50, so 5,050. So this is incredibly clever. It's a very nice observation, and in fact, it's going to allow us not just to talk about the sum of the integers from 1 to 100, but it's going to allow us to talk about the sum of integers from 1 to n, for any n that you would like. So if we want to start with this notion where we're starting with I equals 1 to n of the numbers I, so this expression here means we start with I equals 1, and we add to that, we increase I by 1 every single time, until we get all the way up to n. Maybe I'll include n minus 1 here. We can do the same trick. We can start with 1, and we can pair those together and add them up, and we get n plus 1. And if we add to that 2 and n minus 1, well, those two numbers add up to n plus 1. And we keep doing this. And so we ask ourselves the question, well, how many, so I know that the sum of each of these pairs is n plus 1. There's still the question of how many pairs do I have? Well, if I've got n numbers in this list, there should be n over 2 pairs. And I'm adding up a bunch of n plus 1s. So in fact, we have this cool formula. If you want to add up the numbers from 1 to 1,000,000, you plug in 1,000,000 for n here, and you just get the answer. So pretty nice trick, something that comes up kind of naturally when there are when we're looking at this summation notation for the first time. A cool kind of fact to observe here is that there are also general formulas for, say, the first thing that we were doing. So formulas exist for sum from I equals 1 to n of I squared. So that's something that we were looking at. And formulas also exist for something like the sum I equals 1 to n of I cubed. And more generally, I believe that formulas exist for something like I equals 1 to n of I to the k power, where k is, again, your kind of favorite positive whole number here. I'm not 100% certain on kind of this last claim here, but I believe it's true, and certainly we have formulas for some small values of k, but I think it's true for all k as well. All right, so that's it for this first video talking about summation notation or sigma notation, and soon we'll get into actually approximating some areas.